Hi guys, you are welcome once again to our group tutorials that we do seasonally from time to time. So today also we'll be taking you guys through the Hurwitz Stability Analysis. So this is one of the powerful analytical methods that engineers use to measure the stability of systems. You can, for example, think about a system such as the aircraft that is able to get itself sustained in the air even at minimal turbulence. Alright, so it's as a result of this Hurwitz criterion analysis that engineers are able to determine the stability of a particular engineered system. So my group and I will be taking you guys through how we can apply this to our real-world engineering problems so that we can be able to determine the stability of these systems for effective functioning. Stay tuned and get ready.
Before we dive into the math, let's talk about why this matters. And we are going to start with something exciting. In this case, we are looking at self-driving cars. Imagine you are sitting in a fully autonomous Tesla. You are not touching the steering wheel. The car is sensing the road by itself, making hundreds of micro adjustments every second to keep you in your lane. Now ask yourself this question: how does the car know it won't suddenly jerk left and cause an accident? The answer is simply stability analysis. Engineers in this case model the car's steering control system as a mathematical equation, which is also a characteristic polynomial. In our case, the equation we are dealing with is x to the power 3 plus s plus 2, which is equal to 0. The equation here just tells us everything about how the system responds to the inputs that are being fed into it. In this case, the Hurwitz test lets engineers check it without even solving for the equation, whether the system will be stable or unstable. That's incredibly powerful, right? Because knowing this helps the engineers in solving high-order polynomials that can be extremely complex. The same method is used in aircraft autopilot systems, industrial robotic arms, chemical plant controllers, and even the cruise control in our cars. It's also the backbone of modern control engineering.
So moving on to the problem statement, we understand why this analysis is critical. So let's define our problem precisely. So we are given a characteristic polynomial of a system to be s cubed plus s plus 2 equals 0. So our goal here is to determine how many roots of the polynomial lie in the right half of the complex sp. So why does this matter, if you may ask? In the control theory, if any roots, also called poles, lie in the right half plane, the system is unstable. So this means that instead of settling to a steady state, the output of the system will grow without bound. For a car steering system, this means that the car will veer off road. Then for an aircraft, it will mean catastrophic loss of control. So our mission here is clear: count the roots in the right half plane using the Hurwitz method without actually having to solve the polynomial.
I'm Precious Anna, and I'll be taking you through the coefficient identification. So let's start building our Routh table. The first thing is to identify the coefficients of the characteristic polynomial, and in this case our polynomial is s cubed plus s plus 2 equal to 0. So let's write out our polynomial from the highest term to the constant. The first one is s cubed, which has a coefficient of 1, and then s squared, which has a coefficient of 0, but then it's a missing term. Then we have s, which has a coefficient of 1. Then we have s raised to the power 0, which has a coefficient of 2, which is the constant. So the complete coefficient sequence is 1, 0, 1, 2. And an important rule in control theory is that if a coefficient is missing or negative, it is an immediate red flag. This should tell us that the system is already unstable even before we build the table. And as we can see, the s squared term has the coefficient missing, and this will cause us a big problem.
Now that we have the coefficients, let's find the first roots of the first root is coefficient from forward power tense, and the second root is coefficients from the moving power tense, and the table how you are going to compute the values of that. And this, after this, we are going to run some very important calculations. Okay. The first element of the S squared, okay, which is 0, is going to help us find the second element of the same S squared. And to do this, we are supposed to divide by this term. And division by 0 is mathematically undefined. So which means we can't proceed. So what do?
We are going to be talking about the special cases and solutions. This is a really fascinating part of the Hurwitz method. What happens when things go wrong? And this is a situation called the 0 in the first column special case. When the first element of any row turns out to be 0, we cannot compute the next row normally. If we try to divide by it, we get infinity, which makes no mathematical sense. So engineers developed a clever workaround called the epsilon method. So basically the idea is simple but elegant. Instead of 0, we substitute a very small positive number called epsilon, written as this, where epsilon approaches 0 from the positive side. Think of it like this. Imagine you're driving on a road and there's a pothole. You can't drive through it, but you can go just slightly around it. Epsilon is that slight detour. It's close enough to 0 and the math remains valid, but it's not 0, so we can still divide. The substitution allows us to complete the entire Routh table, and then after all the calculations are done, we evaluate what happens to our results as epsilon approaches positive 0. The signs of the terms in the first column reveal the stability.
Now let's move on to the row calculation. Now with the row calculation, we put the epsilon method to work and compute the x1 row. This is the heart of the calculation. With the epsilon in place of the 0, our updated table looks like this on the slides, with the s cube row having a figures of 1, 1, and the s square row having a figure of epsilon and 2. To compute the first elements in the x1 row, we use the Routh cross multiplication formula. So the x1 elements becomes epsilon times 1 minus 1 times 2 all over epsilon, which when we simplify become epsilon minus 2 all over epsilon. Now here is the key insight. As epsilon approaches the 0 from the positive side, what do you think the epsilon minus 2 all over epsilon will approach? Well, for epsilon minus 2, it approaches negative 2 and epsilon approaches 0 positively. So the whole expression approaches negative infinity. That means that the sign of the x1 row becomes negative. The change of sign from the s squared to x1 means that there is a negative change. So it's changed from positive epsilon to negative epsilon minus 2 all over epsilon, which is very significant because every sign change in the first column of the Hurwitz criteria table indicates one unstable root in the right half of the plane.
Now let's put everything together by constructing the complete Routh table. At this stage, all 4 rows have been successfully filled. Notice that in the s square row, we introduced a small positive value, epsilon, to handle the 0 and allow the calculations to proceed. Moving down to the s1 row, we apply the Routh formula and obtain the expression epsilon minus 2 over epsilon, which becomes negative as epsilon approaches 0 from the positive side. So now, if we focus on the first column of the table, we can clearly observe the sign pattern: positive, positive, negative, and positive. This changes in sign is very important according to the Hurwitz criterion. Every sign change in the first column corresponds to a root in the right half of the S-plane.
Analysis and conclusion. Let's count those sign changes carefully. The first column sequence is positive, positive, negative, positive. So change 1 occurs from positive s exponent 2, which is the epsilon, to the negative exponent 1 row, which is epsilon minus 2 over epsilon. That is one sign change. Change 2 occurs from negative S1 rho, which is the epsilon minus 2 over epsilon, to the S exponent 0 rho, which is 2. That is the second sign change. So total sign changes is 2. By the Hurwitz theorem, the number of roots in the right half of the S-plane equals the number of sign changes in the first column of the Routh table. Since we have 2 sign changes, there are 2 roots in the right half plane. So our conclusion: the system is unstable. In our self-driving car analogy, this control system as modeled by S exponent 3 plus S plus 2 is equal to 0 would cause the car to become progressively more erratic over time rather than converging to smooth, stable behavior. Engineers would need to redesign the controller, testing gain values or adding compensators to push those roots back into the left half plane and achieve stability. This is why Routh house is so valuable in the design stage. It catches instability before a single physical prototype is ever built, saving enormous time and cost. Thank you
for taking us through how to actually determine the stability of engineering systems using the Routh criterion analysis. Yeah, so according to our presentation, we got to know how to use the Routh criterion analysis to determine the stability of engineering systems. So if you followed carefully, we learned that with the characteristics polynomial from our transfer function of the system, we can generate a table technically called the Routh table that will help us to determine the stability. And having the table, we can determine the stability by checking the sign changes in the first column of the table. So with the characteristics polynomial, we can develop a structured table, which is the Routh table, that we can use to check the stability. And we do that by checking the first column, how the sign of the values keep changing. So if the sign keeps changing from positive to negative, then we can know that the system is actually unstable. And in the course of getting this structured table, if we get a 0 in the first column, then we are going to apply the epsilon method to allow us to continue with this generation of the table. So yeah, that is basically how to use the Routh criterion analysis to determine the stability of engineering systems. Thank you, and I hope that you learned something.